The evaluation results tell a devastating story about our first supervised learning model. We achieved 400 ELO rating, which places the model below beginner level chess players. Even more concerning, our model lost all 30 games against Stockfish across all difficulty levels from beginner level 1 up to expert level 10. The critical insight is shown in the overfitting table. Training set policy accuracy reached 79.5%, seemingly excellent, but validation accuracy only achieved 26.7%, representing a 52.8% generalization gap. This is textbook overfitting. The model memorized training positions without learning generalizable chess principles. What's more, when deployed against stockfish, the model generated completely invalid moves below 1% meaningful accuracy. It didn't just play weak chess, it played illegal chess. The root cause is clear from our training curves. After Epoch 8, validation loss began increasing from 3.92 to 4.44, while training loss continued decreasing from 3.13 to 1.57. The model was fitting training noise, not learning strategic patterns. This failure motivated our investigation into regularization and data quality, leading to fixes we implemented. We identified multiple interconnected failures. Overfitting, the training loss graph shows a divergence after Epoch 8, where training loss continued decreasing while validation loss began increasing. This is classic sign of a model learning training specific noise rather than general patterns. Insignificant regularization. The model had no dropout, minimal weight decay, and only batch normalization, with 2.5 parameters per training example, dramatically higher than the recommended 0.01 to 0.1 ratio. The model had too much capacity to memorize rather than learn. Most damning, when evaluating against Stockfish, the model generated illegal moves with less than 1% valid accuracy. This means even the 26.7% validation accuracy was misleading. The model wasn't learning chess at all. All issues combined to create a complete failure: architectural overfitting, numerical instability preventing learning, and a model that couldn't even generate legal moves. For overfitting, we are scaling from 1 million to 10 million positions, dramatically improving the parameter to sample ratio. We are also diversifying the training set with multiple game sources, classical games across different time periods, as well as rapid chess and bullet chess games also included. And we've implemented strong regularization. Dropout zero point 0.3 prevents individual neurons from memorizing patterns. Weight decay 5 to the power minus 4 penalizes large weights, and gradient clipping stabilizes training. For invalid moves, we'll add legal move masking to the policy output instead of letting the model output any of the 8192 moves. We'll mask illegal moves and force selection from only legal options like any game environment does. This ensures evaluation makes sense. The model can only play valid chess. Key insight: we are not redesigning the architecture, we are fixing data quality, numerical stability, and adding constraint satisfaction. This surgical approach preserves what's working, that is, ResNet backbone, policy, or value heads, while removing obstacles to learning. On the other hand, we have developed a strong evaluation setup that helped us find out all these issues. Our evaluation methodology uses Stockfish's built-in difficulty level, just calibration points. Stockfish level 1 plays at around 800 ELO, level 5 at 1600 ELO, up to level 10 at 2600 ELO, which is superhuman. We play our model against each level and look for where it achieves approximately 50% score. At that point, ELO ratings are mathematically equivalent. The ELO calculation uses the standard formula: ELO estimate equal to opponent ELO plus score minus 0.5 times 400. If our model scores 40% against level 5, 1600 elo, it comes out as 1560 elo based on the math. This is standard chess rating calculation. However, there is a critical limitation. Our result use only 3 games per level. With just 3 games, the confidence interval is huge. That is plus minus 100 elo. We give at least 20 plus, we need at least 20 plus games per level to achieve statistical validity. This is why our 400 elo result comes with a plus minus 100 margin. It could realistically be anywhere from 300 to 500, which is still very bad. The code implements this via the Stockfish Elo Evaluator class, which handles engine initialization, move legality validation, and the bracketing algorithm. Future improvements could include scoring move quality, not just win or losses, uh, analyzing opening versus endgame performance, and implementing Glico 2 for a more sophisticated rating adjustments. Thank you.